All right, students, so we're going to be doing conditional probability, all right? And this is where we're really going to emphasize the word given, all right? And we're going to spend 2 days on this, all right? So conditional probability is the probability of event B, probability of B, given that event A, probability A, is also occurring, all right? So this is the notation, all right? Probability of B given A, and that's exactly how you read it, the probability of B given A. And here's a really cool, fun formula that we got going on here, all right? So the probability of B given A is the probability, we'll just write prob, that A and B happen over the probability that A happened. All right, so not too bad, especially as we go through these examples. Hopefully it makes a lot of sense and you guys have a good time. So we have a scenario 1, all right, and I'm going to admit scenario 1 and scenario 2, they're incredibly basic scenarios, all right? You can really just solve these problems by thinking about it, but it's really just getting comfortable with the notation and getting comfortable with the thought process. That's more the concern right now, all right? So if marbles are randomly chosen one at a time and replaced, what is the probability of choosing a blue marble given that we have already chosen a green marble? All right, start with how many marbles in our bag after the green marble was chosen. All right, so again, incredibly basic, but nonetheless. All right, so we have 3 green and 7 blue marbles. All right, so there's 10 total, I just spelled total wrong, total marbles. All right, so this is the ultimate goal, is to use this. All right, it's the probability we choose a blue marble given that we have already chosen a green. So first we are going to calculate green and blue. All right, so get a green on first pick. Well, there's 3 green, so it's going to be 3 over 10. All right, replacing it. All right, we're going to emphasize this a lot, but since I'm replacing it, it's independent. All right, and then we replaced it, and then we get a blue marble. There's 7 blue marbles out of 10. All right, and then you just multiply straight across. (21 over 100). All right, so that's the probability you get a green and then a blue. Step 2 is we're just going to probability of drawing a green marble, which we already did, was 3 over 10. All right, so put it all together. The probability of blue, given that we got a green, is going to be the intersect. We're just rewriting this, store it to our brain, which we got 21 over 100 over 3 out of 10. All right, a fraction over a fraction. There's a bunch of ways to do this, but what I like to do is just kind of break it down. A fraction over a fraction seems very scary. All I'm going to do is rewrite it. And instead of using a fraction bar, I'm going to change it to that notation. All right, so again, all I did was change this fraction bar to that division symbol right there. All right, because then all we do is keep, change, flip. All right, so we keep the 21 over 100, change the multiplication, and then flip the last one. All right, and then we're going to get 210 over 300. All right, and then reducing, helping you guys with some reduction facts, is that the zeros at the end go away. So we have 21 over 30. A 7 can be factored out of both of them, so I get, not a 7, a 3. So I get 7 over 10. All right, that's the answer. All right, and that makes sense. All right, what's the probability I get a blue given that I already got it in green? Well, it's 7 over 10 because I replaced it. All right, so we could have figured this out in 2 seconds. But it's really just the process that I'm more concerned about, the formula, all that fun stuff. All right, so scenario 2 is the same thing, except now we're not going to replace it. What is the probability hold on before I get too excited. And remember, not replaced goes with dependent. that says dependent. All right, so what is the probability of choosing a blue marble given that we have already chosen a green marble? All right, so step one, notice that green, I get a 3 out of 10, but getting a blue one next, it's not 7 over 10 anymore. There's still 7, but now it's 7 over 9 because I kept a marble. Multiplying straight across, I'm going to get 21 over 90 this time. And then if we want for fun, we can reduce this now. 7 times 3, that's a 30 times 3. The 3's cancel each other out. So 7 out of 30 draws would I get a green, keep it, then get a blue. Now probability of just getting a green, flat out just getting a green, is 3 out of 10. All right, now put it all together. Let's see what happens. It's going to be the intersect. Over just getting a green. So again, we're going to have a fraction over a fraction. And remember, all I'm going to do is rewrite this. I'm going to rewrite the division symbol. So that just turned into that. So keep, change, flip. Keep the 7 over 30. Change to multiplication, flip to that right there. We're going to get 70 over 90. Which reduces to 7 over 9. All right, again, we could have figured this out quite quickly. That was 7 over 9. Let me rewrite 7 over 9. But it was more of just the process of coming to that conclusion. All right, and notice how it changed. We went from 7 over 10 to 7 over 9. Because one we replaced, one we did not. So in scenario 1, they were independent. And when probability of B over A equals the probability of B, that means that they're independent, all right? So like, it didn't matter. The probability in the first example of choosing, let's write just blue, was 7 over 10. So it didn't really matter what happened. The probability of B happening was 7 over 10. It didn't matter the given. That's independent. Now let's discuss why this is true. Because let's focus on this part right here. The probability of A given B. Remember, independent. This is the multiplication rule of probability A times the probability of B. All right. A given, or A and B happening, you just multiply them together. All right, if that's the case, then this probability of B given A, I'm just going to replace the numerator with the probability of A times the probability of B. It's still all over A, or the probability of A, I should say. The probabilities of A cancel out, and bada bing, bada boom, that's just why we're left with the probability of B, which shows why they're independent. So if this equals this, it means it's independent. I wrote independent a bunch of times. All right, so that's it for this video. Stay tuned for some more exciting stuff.